Hi everyone, and welcome back to the lab. In this video I'll be making hydrazine sulfate using a method that I haven't seen anybody else use on YouTube or on forums or anything else. So I think this will be kind of interesting if you're interested in hydrazine sulfate, or if you've made it before, or if you simply need some for something else. Speaking of which, I'll be using hydrazine sulfate in a number of upcoming videos, so that's kind of why I'm making this video. I like to show you the chains of things, so if I'm using one thing, I'd like to show you how to make the things that I need for this video. That way you can sort of follow along if you'd like, or it just sort of proves to you that I do get most of my stuff initially from OTC sources. Anyway, this is hydrazine sulfate. If you're here, I probably don't need to explain to you exactly what hydrazine sulfate is. Standard basic amine, protonated by an acid. Sulfate salt, no problem. It's useful for a lot of things. It's a reductant. It's a rocket fuel, and you can use it to make silver mirrors and all sorts of things like that. Interesting compound, and there's a few different ways of making it. It's kind of tricky to make, actually, so there's a lot of things out there about how to make it. So there are three general methods. This first method, I believe UC235 exemplified very well on YouTube, in fact, where you have a basified solution of hypochlorite and you add urea to it, or actually you add it to urea at a slow pace, and you end up performing what's known as a Hoffman degradation, which, if you'd like to know more about, his video explains it very well. He's got the mechanism and everything else on there. It's a Hoffman degradation of urea, and you end up with hydrazine. Then, of course, just a workup with sulfuric acid. The second method, I believe, is best exemplified by Nerd Rage, which is essentially just mixing bleach and ammonia. You end up with some various chloramines and things like that, and eventually hydrazine in solution, and then you can extract the hydrazine as the ketazine by reacting it with methyl ethyl ketone, which forms an insoluble compound called the ketazine, right? And you can separate that out and then hydrolyze the ketazine and end up with hydrazine sulfate. And the third method, I don't really know who did this. I think my family did it, something like that. I don't remember, but it's the chlorourea process, where you essentially chlorinate a concentrated solution of urea to form a chlorourea intermediate, and then you hydrolyze that all at once with sodium hydroxide to form hydrazine, and then it's just worked up with sulfuric acid. In fact, you could work up any of the end products of these reactions with sulfuric acid or the methyl ethyl ketone, followed by extraction and then sulfuric acid. It just depends on the purity that you're looking for. Personally, I like the MEK method, but that's just me. So the method I'll be using is sort of like a mixture of all three of these in reality. It involves mixing a very slightly basified hypochlorite solution with urea and holding it at a low temperature before running the full up hydrolysis of the chlorourea intermediate, kind of like this one and this one at the same time. So what happens is you mix a very small amount of base, just to keep the whole thing basic, with sodium hypochlorite, and then the hypochlorite is kept at -10 or so in the freezer. I did it at 0 last time and the yield was okay. And you add an equally cold solution of urea very slowly over time, or the other way around, you add the sodium hypochlorite to the urea, obviously, because you don't want to over-oxidize the hydrazine. But anyway, and you end up with this chlorourea intermediate in a solution, and then you can hydrolyze it all at once with sodium hydroxide, bring the thing up to a nice high temperature to make sure the reaction goes to completion, and then work it up any way you want, either with the acid or with methyl ethyl ketone. So anyway, I've got that all set up and ready to go, so I think I'm going to film it, and then you guys will see how to make hydrazine sulfate for a fourth way. Let's get to it. So the first solution I need to make is the urea solution, which I have here. This is 189 milliliters of water, distilled water that is, with 126 grams of urea. We're trying to keep as many metals as possible out of this reaction because they catalyze the destruction of the intermediate products. So try and use as pure urea as you can. I'm just using fertilizer grade here because it's cheap, and I can use large amounts of cheap chemicals, and that doesn't really bother me, but always try and use distilled water for this, which I have. Anyway, this is really cold. I'm going to heat it up in the microwave a little bit to get that in solution, and then we'll make solution number 2. The next solution is 8 grams of sodium hydroxide in an equal amount of distilled water. So 8 milliliters, which is also, of course, 8 grams. And stir that till it dissolves. Next, it's time to break out the big glass. I've got a 4-liter Erlenmeyer flask here, very large, genuine Pyrex. That was not cheap. Then you're going to need an equally gargantuan stir bar to break down all that foam. So here we go, 4-liter flask, big old stir bar, and I'm just going to give this a quick rinse. Alright, here we go, and we'll put the stir bar in very carefully. These big flasks are very easy to break by accident doing things like that. Alright, so into this I'll need to put 1,562 grams of the 10% hypochlorite solution, which is just this fresh bottle here of HTH liquid pool chlorinator. And as you can see by the ingredients, 10% hypochlorite. So what I'm going to do is fill up this freshly washed and tared 500 ml cylinder here, and then figure out the density of this stuff so I know exactly how many milliliters 1,562 grams is. So 500 milliliters is 575.8 grams. So we can go ahead and add this to the flask here. If 575.8 grams is the weight of 500 milliliters, its density is 1.1526. So that means if I need 1,562 grams, so 1560. Oops, it's hard to use these with gloves. So that's actually 1,356 milliliters. So I already have 500. So this 500 and then a 356. See how well my pouring hand is calibrated. Set that down. I'd say that's close enough. Okay, and this needs to go in the freezer for chilling down to as cold as you can get it. So it should start to freeze. It's about minus 10°C if I recall correctly. My standard household freezer goes to minus 20, so it shouldn't really be much of a problem as long as you have one big enough. As you may have noticed, because of the condensation, like on this cylinder and stuff, I do keep my hypochlorite typically in the refrigerator, which helps prevent decomposition, so this stuff stays fresh. Okay, now that the urea has dissolved, I'm going to prepare the reaction vessel by using this 2-liter beaker here. Oh, this is the reaction vessel. I will add the sodium hydroxide solution to the bottom of that. Still warm, hasn't quite dissolved completely, but it's fine for now. And then I'll add the urea solution to it rapidly, as so to stir them together. There we go. And now this will also need to go in the freezer to cool down. Okay, so these have been in the freezer for a little while, and you can see this solution here has partially frozen actually. This is the urea. The goal now is to add all of this, the hypochlorite, to the urea solution, not the other way around. So this big one into the little one, over a period of time, such that we minimize the amount of decomposition that happens. So that's got to be, of course, carried out at low temperature. I've got a thermometer here. This is unfortunately a Fahrenheit thermometer because my Celsius thermometer, or my other Celsius thermometers, don't go this low. So I'm going to call it that as long as this is under 25 degrees Fahrenheit, then it's okay to add the next portion, and that's going to take approximately 20 minutes in between additions. I'm going to be adding 100 milliliter portions as measured by the speaker. Again, it's approximate, doesn't have to be super accurate, but we just want to space this out to minimize the decomposition. You can't add it all at once. So I'm going to put a stir bar into this solution here. Turn on stirring, even though it's not going to be able to do anything until I add the hypochlorite. And then go ahead and measure my first 100 milliliter portion of hypochlorite. Again, freezing cold. And go ahead and add that, and we want to stir this as vigorously as possible. And you can see that the reaction is quite exothermic. That's already melted. Temperature of the solution has climbed to approximately 20 degrees Fahrenheit. I'm going to go ahead and put this back in the freezer. Alright, and you can see now we have a clear, well-mixed, cold solution, and we need to keep that as cold as possible, so I'm going to put this back in the freezer right now. And I'll be back as soon as this gets down below 25 Fahrenheit for the next 100 milliliter addition. Alright, it's been about 15 minutes, and this is cooled sufficiently. We're at like 18 degrees Fahrenheit. And the temperature shoots up a few degrees. Alright, back in the freezer. A little over 300 in. A little more than 1,000 to go. Number 7. In between additions, I'm going to prepare 2 additional solutions. This one with 152 grams of sodium hydroxide in an equal amount of water. Be careful when you add this because it may start boiling. It will get very, very hot. And we'll just let that dissolve. And 1 gram of unflavored gelatin in approximately 10 milliliters of water, whatever it takes to fully dissolve it. You'll need to warm this up a little bit. And we'll just get that stirring. Alright, we're getting close to the end here. This is either the second to last or the last addition. Depends on how close my measurements were. Well, we might actually get... yeah, I think this is the second to last. Okay, it is now time for the last addition, and as you can see, I left this in the fridge, or the freezer overnight. It was like almost 4 in the morning when I stopped, so I needed to take a rest for a little while. But anyway, it'll be okay when it's frozen. For the last addition, we're going to do the opposite and actually add this solution back into here to get it all into the reaction vessel for the next step. So it's kind of good that it's frozen now because it will minimize the side reactions that happen in the first stages of this pouring operation where I'm adding the urea to the hypochlorite rather than the other way around. You can see it's like 8 degrees Fahrenheit there. Pretty chilly. Okay, the ice has mostly melted, and I've attached a funnel to the top to catch any foam. In previous runs, the foam never exceeded the volume of the flask, but this is a 10 times scale from the previous run, so sometimes things don't quite scale as well due to the surface area to volume ratio of the flask. So I've got the funnel there just in case because it will foam a little bit. And like I said, the foam should be contained in the flask, however, the funnel is there just in case. Now, I've got the funnel taped in with this packing tape here. I bought special rubber tape for that, but I can't find it to save my life, so we're going to have to just go with that. And if there's leaks, well, there's going to have to be leaks. So this is the step where we hydrolyze the chlorurea and actually form the hydrazine. So first I'm going to add the gelatin solution. Just pour it straight down the funnel. Maximize stirring. And then the sodium hydroxide all at once. And then we're going to start heating on maximum to drive the reaction, and we're going to heat this until it begins to boil, until all the foam has completely subsided. As this warms up, we are making the hydrazine and releasing carbon dioxide, but also decomposing a little bit of the hydrazine in the process. So we want to minimize this thing's exposure to the atmosphere, especially if the foam comes over the top. As you may be aware, the rate of reaction is affected by temperature, so of course this being fairly cold, the rate of reaction is going to start out really slow and slowly pick up speed as it gets hot. So I'm leaving the funnel in place just in case. But in previous runs, I've predicted the foam to only rise to about 3 liters on a 10 times scale, which is 300 milliliters in the last run. Okay, so here's the part where it's going to foam the most. You can see it feels like it's about 50 or 60 C right now, and we've increased reaction volume to about 2,500 milliliters, although the foam is rapidly popping. You can see now the foam is rising quite rapidly, and we're really reacting now. It's about 60, maybe 70 C, and probably more like 60. But you can see we're at about 3 liters of total volume. This is where it stopped last time I did it. I'm going to increase the stirring, which should help beat down some of that foam. And it looks like we're keeping it in check right around 3,500 milliliters.
Still plenty of room before the top, and then also, of course, I got the buffer funnel there. But yeah, it looks like we're subsiding now. Yep, and now the foam is rapidly going down. I think the reaction is essentially complete. If I turn down the stirring, so the foam continues to rise. Nope, but you can see that this has pretty rapidly gone to a from an amber to completely clear. See that? That just happened. And there you go. Now we have a solution of hydrazine. And it's just beginning to boil, so I'm going to turn off the hot plate, and I'm going to get a covering for the top of this flask. Get rid of this mess, and protect it from oxygen. And there we go. A flask of a hydrazine solution, among other things, and all I'm going to do is let this cool down enough so that we can add the methyl ethyl ketone without a whole lot of boiling. So I'll be back for this in approximately 20-30 minutes. Alright, so the hydrazine solution's been cooling in that bucket of water. So I started with lukewarm water, followed by cold water, just to reduce thermal shock on the flask. That should be just warm to the touch now. The hot plate is also cooled down, so I can use it now as a stirrer. And I've measured out 400 milliliters of methyl ethyl ketone, or 2-butanone, to form the azine. We'll get the flask out of the bucket here. And yep, I think we're cool enough to add the 2-butanone, so I'm going to get this stirring ever so gently, and then we're going to pour this in. There we go, 400 milliliters of 2-butanone. And again, I've got the watch glass on the top. And so to form the azine now, I'm just going to crank up the stirring a little bit and keep this well agitated for an hour or two as it cools down. And yeah, then we can go ahead and extract it. So what we're doing with the methyl ethyl ketone is reacting it with hydrazine to form an insoluble product which will oil out to the top. So one equivalent of methyl ethyl ketone reacts with hydrazine here. In fact, hydrazine reacts with pretty much all ketones to form this, which is a hydrazone. And you can see it's hydrazine ketone, right? It's a hydrazone. So this hydrazone here is actually fairly soluble in water still, you can see by this free amine here. So you can react it again though with another equivalent of the ketone to form this, which is the dihydrazide. This is like methyl ethyl dihydrazide. And it's got this azine bridge here, which makes the whole thing essentially nonpolar. So it floats to the top, it's very insoluble in water, and we can go ahead and extract this. And this will actually hydrolyze back to hydrazine and methyl ethyl ketone in the presence of sulfuric acid. So we will pretty easily be able to make the hydrazine sulfate salt from that. Something to note while I'm waiting for this azine to fully form is that you can kind of tell the status of this reaction based on how it looks. When I first add the methyl ethyl ketone, you have a clear solution and then a clear amount of methyl ethyl ketone floating on top. And then when I start stirring it, of course, it agitates the ketone. You end up with a bunch of suspended little blobs, and it becomes cloudy. But after a little while, you'll notice that that cloudiness goes away and it becomes a completely clear solution again. And the reason for that is because the hydrazone is forming first, and the hydrazone is much more soluble, and so everything gets pulled into solution. But a few minutes later, you'll notice that it'll get cloudy again as the azine compound forms, the diazine compound, which is clear, and it floats to the top, and you can see there's a little layer of it kind of bouncing around right there already. But also it takes on this sort of yellow color, and that's just because of aldol condensations that happen with ketones in basic environments. It's just a byproduct, and it won't be a problem, but it does give it quite a bit of color. And yeah, so we've got about another hour to go stirring this, and we should have completely formed the azine, and we can work that out. Alright, so I've stirred this for about 2 hours. It's coming back down to room temperature. It's just barely perceptibly warm now. And I don't know if you can see, but there is a decent layer of azine on that down there. Looks to be about 400 milliliters, and a cloudy solution underneath. Now that solution will remain cloudy probably because it has an emulsion of the azine in it. I think that's why it stays cloudy, but honestly, I've never been able to get any more azine out of it. So what I've done before is, after filtering and separating this out, I saturate this solution with sodium chloride or potassium carbonate. Actually, I haven't tried potassium carbonate yet, but I tried sodium chloride last time, and it didn't work. So maybe I'll try again this time with sodium carbonate on a small scale with a sample of this. But for now, we're just going to take this azine layer off, and that's what we're interested in. So using a step funnel is pretty easy. Of course, just make sure the stopcock is closed before you start draining stuff into it. Now, the azine compound here is fairly toxic. It's probably carcinogenic, so just be careful when you're doing this. I hope this won't run down the side of the flask, but it may very well, and I'll have to think of a different solution. Oh, it looks like we're going to be good. The azine has a peculiar smell. It's really sweet and sort of strange. Definitely different than MEK. You can definitely tell something that. So I'll give this a minute to separate. As you can see, we've got the azine layer here and a water layer underneath, and in the middle there's like bubbles of one and the other. We'll just wait for those to subside. You can see it's happening right now, and then I can drain off the water layer into the beaker, and then the azine into this, and then refill and do it again until that's empty, which should take 3 or 4 runs. Alright, just a little bit there. That was the final extraction. For a grand total of just over 300 milliliters, it looks like, of the 2-butanone azine. Ready for hydrolysis. To see whether I might be able to recover additional ketone azine by saturation with potassium carbonate, I'm going to try a small sample here of the liquid that we poured the azine off of. I'm just going to add a little bit to this Erlenmeyer here. So also to this flask, I'm going to add a spoonful of technical grade potassium carbonate and then shake it vigorously to see if that breaks the emulsion. Even if it does, though, I suspect that it's going to take too much potassium carbonate per given volume of the liquid here to make it worthwhile extracting the rest of the azine that's in there. So let's try this. Seal her up. Give her a good shake. I'll give it a minute to let this dissolve and see what happens. To hydrolyze the dihydrazide compound, the methylethyl-ketazine that is, it's going to go in this flask here, and we'll add sulfuric acid and water. And the sulfuric acid will hydrolyze the compound back to hydrazine, which will react with the sulfuric acid, forming hydrazine sulfate, which is what we want, and then methylethyl ketone. And the methylethyl ketone, being the lowest boiling point component of this mixture, will boil out first, and I'll just collect it using this condenser here. It's just a 300 millimeter Liebig, and I'll have a receiver on the end there. So to do that, I've got here the 300 plus milliliters of the methylethyl ketazine. I have also 200 grams of water and 200 grams of 93% sulfuric acid, and that should do the trick. So first we'll make the sulfuric acid solution. Remember, always add acid to water. This is going to get hot really quick. If you only have a one-neck flask in certain sizes, it's helpful to have a really long stem funnel like this, so when you charge things, you can charge them directly down the still head without having to take this apparatus apart, and the long stem of the funnel bypasses the condenser, so you don't contaminate the condenser with whatever you're running down there. So I'm going to add the methylethyl ketone dihydrazine compound here. There we go. And then I can slowly begin to run in the sulfuric acid. Just going to be careful that I don't initiate boiling. We'll get the condenser water going. Alright, pause for a second to allow it to cool down a little. And you can already see there's a substantial precipitate of hydrazine sulfate in this flask. So now I'm just going to begin heating and stirring
and distilling off that MEK. First swap out the still head here. Meanwhile, over here on the dirtier side of the lab, I did find that in this experiment here, adding 5 grams per 100 milliliters of the solution caused a small additional amount of the azine to be produced. If my camera will focus on it. There we go, you can kind of see it up there. So I'm going to add a total of 100 grams, since there's about 2 liters, of potassium carbonate to this giant flask here with stirring. That looks like this. And that should allow me to separate additional azine. We're at 100 grams, and we'll just stream this slowly in with strong stirring. Not too worried about the cost, since potassium carbonate is quite cheap. Not as cheap as sodium chloride, but hey, if this does the trick, we'll see how much more azine we can get out of this. We're just now getting distillate coming into the head, and dripping out now right into the collection bottle. I'm just going to save that methyl ethyl ketone as just stock for future use with hydrazine sulfate preps. That way I don't cross-contaminate anything. So I've been boiling this for about an hour now, and I've got a little over 300 milliliters of methyl ethyl ketone recovered. And you can tell we're starting to get to the end because of the temperature that the still head would be, but unfortunately my thermocouple reader doesn't have a battery right now, so we're at 91. The majority of the distillation was at 70, which corresponds to the boiling point of methyl ethyl ketone, and then it jumped up rapidly to about 80, which is about the azeotrope of methyl ethyl ketone in water, as may be influenced by sulfuric acid. And now we're at about 91. I'm going to stop at about 95. That means we're just going to get some water over. And that's also evidenced by the phenomenon occurring here. When the drips of distillate enter the main puddle, you can see they're flying to the bottom, which means they're denser, and that's water. So I'm going to go ahead and stop this distillation, and it's pretty easy. Let's turn the mantle off. Sorry for your ears. There we go. And I'll let that cool down on the condenser for a little while, and then once it stops boiling, I'll get it on this cork ring and we'll stick it in the freezer to precipitate as much hydrazine sulfate as possible. You can already see there's quite a bit on the bottom there. So I'm set up here for vacuum filtration, and the hydrazine sulfate solution has been sitting in the freezer for a while, and so we're going to go ahead and filter whatever precipitated out of that. And here it is, nice and cold. Good crop of hydrazine sulfate crystals on the bottom of that. Just fish the stir bar out here using this magnet. Convenient. Okay, so sorry about the noise. Alright, and then I'll swish this with some ice cold water, and we'll get it through the hydrazine sulfate up here as well, which will wash the sulfuric acid from it, and then we can dry it. Alright, so here's the cold water. You can see there's a little bit of ice forming in it already. I'm just going to pour it into this flask. And we'll swish it around to get it off the walls. Go. Cover it a little bit more, and then all at once, right into there. And you can see the pink color of the sulfuric acid rapidly disappears with it. There we go. Alright, so I've had it on the suction for a few minutes. I am now going to transfer it from the funnel to to this glass pan here, so I can further dry it over a water bath. There we go. It's fine white crystals. Looks sort of like wet snow almost. And this will sit on a water bath. I'll get this set up in a second to dry the remainder of the water off of it. This here is the reaction flask, which had the 100 grams of potassium carbonate added, and you can see that there's a little bit more azine floating on top right there. I'm not sure if it's really worth extracting. It looks to be like maybe 20 milliliters or so, which would increase my yield by a little bit, but again, I probably should add the potassium carbonate before I extract the azine. That would have made a lot more sense. However, this was a kind of a test, so if you're going to do it, you may want to think about doing that. Also, the yield can be increased marginally by further boiling this solution down and then crystallizing it again in the freezer and repeated filtering. So we'll maybe boil it down to half and refreeze and stuff like that. But hydrazine sulfate isn't very soluble in water when it's cold. So that, and then of course the common ion effect with the sulfuric acid that's in there, it's not really worth it, especially considering that the stuff that's going to come out of here is going to be pretty full of impurities as well. Alright, the powder is dry, and we can now put it in a storage container and weigh it. See what the yield was like. Now this is the final product. It's a free-flowing, glittering white powder, finely crystalline, and it's hydrazine sulfate, of course. This is 73.6 grams of hydrazine sulfate, which corresponds to a 24.9% yield. It's pretty terrible, actually. But as always, patents don't actually have to be correct. They just have to be sold. So the 75% yield they claimed in a patent, I was never able to recreate. This is the third time I've tried it. So anyway, I thought I'd just make it on a full scale to show that it does in fact work. It's just that the yield is pretty low. Most hydrazine sulfate syntheses have low yields. I think the highest I've ever seen was 56% anyway, so not too terrible considering. Anyway, that's about all I have, so thanks for watching. If you liked this video, please press the like button. If you'd like to leave a comment, please do, and I'll try and answer as many as I possibly can. If you want to see more of these videos, press the subscribe button, and also I've got a Patreon account, so if you'd like to donate 50 cents or something like that toward me making new videos, because this stuff isn't cheap and I pay for this out of my own pocket, feel free to donate. I appreciate all donations, and there are rewards. You'll get your name and stuff in the title of the videos and things like that. So anyway, thank you very much for watching.